When asked, no one can deny the desire for cleaner and more environmentally friendly transportation methods. The truth is that people are willing to consider these environmentally friendly options as long as they do not conflict with their comfort and convenience. In the 1950s, when the concept of personal rapid transit was still new, Don Fichter, a New York City transportation planner, predicted that people would give up their cars for public transit only if it offered a much shorter travel time from one end to the other than existing systems. A level of performance and flexibility he believed could only be achieved with PRT. In 1964, he published his findings in a book describing how automated public transit systems could be implemented for medium to low density areas. Fast forward to 2023, 70 years later, at a time when there are only 3 functioning PRT systems in the world that provide a service to the people around them. Interestingly, governments around the world do not consider any of these examples to be an attractive solution to the problems posed by their current means of transportation. This scenario somehow tells us that we, as proponents of PRT systems, have not been able to find a way to put our proposal into action. We have not been able to present a convincing argument with evidence that makes our proposals not only feasible, but desirable. Evidence that refutes all of our opponents' arguments, many of which have remained unchanged for over 70 years. What conclusions can we derive from this situation? We need to stop using the same old rhetoric of one solution that will solve all of humanity's mobility problems, and instead present a solution that provides a range of reasonable benefits at a reasonable cost. Taking the first step is always the hardest. At SolarSkyways, we are working on what we consider to be the cornerstone of the entire system. We're working to develop a control system that will safely and efficiently operate a network of as many pod cars as needed, traveling along a guideway that can reach multiple destinations without requiring additional last-mile trips. This control system is based primarily on the work of California-based company Transit Control Solutions, led by engineer Jin Nishinaga, as well as the work of our in-house engineering team, full of talent and creative impulse. Nishinaga and his team have developed control systems for various transportation projects, such as the BART system that currently serves people in Northern California and connects the San Francisco Peninsula with communities in the East Bay and South Bay. The joint project between TCS and SolarSkyways aims to test progressively more complex versions of the control system on scale tracks and vehicles. The scale models we're using provide valuable information about how the system works, with multiple actors and factors in play, which would not be possible using a full-scale version of the system. Only after we are confident that our main control system is robust enough to provide an efficient, reliable, and safe service despite all possible occurrences, can we begin to consider other important design factors such as weight tolerance, speed limits, material durability, etc. The idea is to make the operating scenarios complicated as possible, with variables, contingencies, and other factors to test how the control system would react to all these situations it will encounter in real life. Furthermore, we cannot start visualizing a user experience journey until we are sure that the user will actually be able to input his traveling instructions into the system and that it will respond with an appropriate response to those needs. Therefore, it is of utmost importance to accelerate this phase as much as possible, because much of the future progress of this initiative depends on the positive outcome of our efforts to create a reliable, robust, and secure control system. Our current testing phase will demonstrate that the system is capable of handling its basic operational scenarios, which when transferred to a full-scale, fully functional system, are expected to save significant time and money. After years of talking to public officials and reading research papers and articles about public transit, we have been able to narrow down all of the concerns and doubts people have about PRT systems to three main factors. If a PRT system is to be a solution, it must address these three factors effectively. We call them the three big S's of public transportation, which are scalability, sustainability, and safety. Both in the literature and in our own experience, we have found that the governments that have shown interest in implementing a PRT system in their cities have all expressed concerns about the scalability of such systems. This is because the few examples of PRT systems in operation today are only capable of traveling in a loop, in a circular fashion, and are not capable of reaching any destinations other than those that are already within that loop. In order to grow beyond the loop, not only do the guideways need to be branched out and more stations built, but control software is also needed that is capable of managing the traffic situation when many vehicles are traveling on the guideways at the same time. Now, in 2023, we're not ready yet to build a metropolitan PRT system that covers the area of an entire city. First, we must narrow it down to smaller communities where a train station or airport can be connected to the rest of the community by a PRT system that can provide point-to-point service that currently can only be provided by cabs or Uber-like services. In addition, and most importantly, local communities need to be assured that if they choose to build a PRT system for their city, it will have the ability to expand and connect with the neighboring PRT systems. This approach envisions incremental investments in local PRT systems that can later be connected to neighboring systems to form a larger network. This means that the control system must be able to handle the traffic of all these vehicles entering and leaving several stations at optimum speed. So, in order to talk about scalability, we first need to demonstrate that our control system is capable of handling a high density of travel at high speeds. So far, the TCS team has run a series of computer simulations that allow them to assess the performance of their software. Now, however, we're taking the next step and testing the performance of the control software on a scale model track with up to 20 vehicles running around, whose actual physical components must now interact with the control software and respond accordingly to the instructions given. It is critical to do this type of testing on scale models because it would simply be too expensive to build a track large enough to test 20 or more full-size vehicles at the same time, which is exactly what you need to get a proper idea of what the control system can do. Another reason for running tests on a smaller scale is that we can make the scenarios as complicated as necessary to test the capabilities of the control system in different circumstances. A very important aspect that can be achieved with our control system is the distance of 1 second separation between cars traveling at a speed of 100 kilometers per hour. This is a speed that allows us to be competitive with other current means of transportation, such as light railroads, that have to stop at every intermediate station, while one of our pods can reach its destination without any stops or interruptions at a more or less constant speed. In addition to the ability to allow vehicles to travel at high speeds with a minimum of spacing between them, the high volume of traffic at intersections must also be managed. Our control software is able to coordinate the movement of fleets of vehicles coming from different directions and entering an intersection. They arrive at exactly the right time, at the right speed, so that the flow of traffic at these points is uninterrupted. This is another factor that the control software must handle efficiently for the entire system to provide good service. One of the things that we are testing with the scale models is precisely how we can manage intersections efficiently. After years of research into the economics of public transportation, we can safely say that a PRT system is much more sustainable than other modes of transportation in terms of energy consumption, simply because our small individual vehicles can carry the same number of people as a large train, without having to stop at every station. Which means that every time this happens, we need to use a large amount of energy to get the train moving again at a speed of 60 miles per hour. It takes about 10 megawatts to accelerate a 1 million pound, 700 feet long train to reach mainline speed. The SolarSkyways stations gather 1 or 2 megawatts from their adjacent solar arrays during the day. That's quite enough to accelerate 5,000-pound vehicles from a standstill at 50 to 100 kilowatts to 60 miles per hour for a short time, and then only a few tens of kilowatts at running speed. By storing daytime surplus, we generate enough to power our entire system day and night with clean, renewable energy sources. One of the challenges in developing a control system is that it must be proven to be absolutely safe. There are many methods and techniques to design a complex electronic system to meet the safety specifications set by government institutions. Engineer Jin Nishinaga has been involved in the development of control systems for several very important projects, such as the Bay Area Rapid Transit System, or BART, or the first PRT system to ever be implemented in Morgantown, West Virginia. Nishinaga is combining the various techniques he has learned from these projects and is designing a whole new set of parameters suitable for the conditions of what SolarSkyways is currently creating. In the past, at the time when the BART system was being built, in order to be called safe, a control system had to prove that it was capable of operating with a mean time between unsafe failures of at least 250,000 hours. Now, we are developing the next generation of control systems, which must have a mean time between unsafe failures in the order of 10 to the 9th hours. You have to use a lot of special techniques and methods to achieve this level of safety. None of this work would have been possible had it not been for the fact that SolarSkyways is made up of a group of talented professionals. This video is mainly about the development of the control system, but in parallel, we are also working on the design of the guideway and the bogie. We have come to the conclusion that these three components must function perfectly before any of the potential benefits of the overall concept can become a reality. SolarSkyways' priority is to create intellectual property based on the primary goal of developing these three components. Ron Svensson, the founder of SolarSkyways, knew that this goal required a special kind of leadership and an entirely new way of organizing and planning. That is why Jorge Rodriguez from Toluca, Mexico, an outstanding industrial designer and design theorist, was entrusted with the management of this project. Jorge has a unique talent for quickly understanding the needs of a project and building teams around them. With his design firm, Rothsmass, he recruits specialists from all over the world, depending on what the project requires. In this particular case, industrial designer Gabriela Sanchez was brought in because she has a unique combination of skills with her background in industrial design and her current work as a marketing coordinator for various clients. She was tasked with coordinating the creation of a solid brand image to communicate the team's accomplishments in a visually strong and clear way. Mario Cruz is a Mexican industrial design master's graduate from the University of Cincinnati who has been working with Rothsmass and SolarSkyways since 2018. He has been able to utilize several of the design understanding tools he developed with Jorge Rodriguez to fully understand the project and its complex requirements so that no loose ends are left, and decisive and informed action can be taken. Jorge Rodriguez uses his team to constantly review the needs of the project and find the right way to fulfill them. He also creates different types of communication material to keep our investors, supporters, and the general public informed about the progress of the project. To give shape to the newly formed organization, an executive team was formed, consisting of Ron Svensson, Dr. Furman, Jorge Rodriguez, and the recently added and highly valued engineer, Jin Nishinaga. The executive team has begun planning and designing various test tracks at different scales. However, planning the manufacture of the parts required for these tests and coordinating all the technical decisions made by the executive team is the responsibility of our engineering project manager, Gregory White. Greg is a mechanical engineer graduate from San Jose State University. His talent and leadership skills have come in handy in leading a team of engineers whose primary goal is to build a scale test track and program its navigation control software to demonstrate the basic operating principles of the three components we have been talking about. Greg is joined by Khoa Lam, a software engineer also from San Jose State University, who has become an integral part of our organization because of his unique problem-solving skills. He leads the programming and the navigation control software, along with his colleague, Carlos Ortega, also a software engineer from San Jose State University, whose talent and enthusiasm has been instrumental in helping us accomplish important goals, one step at a time. Finally, mechanical engineer Nya Nguyen, another great asset from San Jose State University, is the latest addition to the so-called core team. He has overseen the construction of intricate designs that must meet stringent performance standards, even at the prototype stage. These four talented engineers form our core team. Jorge is the coordinator between these different teams in this layout. He listens to the specific needs of the teams and must provide them with action paths and tools to help them achieve their specific goals and ultimately advance the entire organization. SolarSkyways is working to develop new intellectual property that is critical to the development of any autonomous transportation system. We have the skills, the discipline, and the people to achieve many great things that will have a positive impact by revolutionizing urban transport. providing key technological and design elements and creating new efficient, sustainable, and convenient travel options aimed at reducing congestion, emissions, and air pollution. This new version of an old concept can improve the quality of life of people and contribute to a greener and more technologically advanced urban environment.